Good evening, everyone. We want to welcome all the schools that have joined from the different parts of the country. Thank you so much for joining. I want to welcome all the teachers that have joined us. Thank you so much for joining. I'm going to ask a volunteer from Nansana St. Joseph. Any volunteer from Nansana St. Joseph or from Stena Hill? Unmute and you lead us in a word of prayer. From Nansana or from Stena, any volunteer, student, you can unmute and lead us in a word of prayer. Yes, Stena, go on. Oh, okay. I'm failing to get Stena. Okay. Okay. Sorry about that. But we want to dedicate this session to the Almighty God, that everything we have planned may go on smoothly. Allow me now to invite our facilitator, Teacher Martha, to take us through. Teacher Martha, you are most welcome. Teacher Martha.
Thank you so much, Mr. Kasuma.
Okay. Yes, you are clear.
Thank you so much. You're all welcome, the teachers on this platform, plus the different schools that are connected. Thank you for connecting this chemistry seminar. And I would love to recognize the teachers that have joined us. Please, if you're a teacher, just introduce yourself briefly such that when we begin, you can always chip in something so that we can all contribute to our learners' success. So if you're a teacher, kindly, you can introduce yourself so that we can know you're here and then we can begin.
Maybe let them raise up their hands and then we can allow them to unmute.
Okay, probably that would also do. Thank you, Mr. Kajua, for the guidance. So kindly, if you're a teacher and you have joined us, just raise your hand and introduce yourself so that we can know who we have here. I think I'm seeing Mr. Kaira, and then I'm seeing Teacher Richard. Sorry, Teacher Brian. So maybe where need be, you will kindly share with us your thoughts on the different things that we are going to be discussing about. So I hope you can all see my screen, and as we all know, chemistry is made up of 3 papers, and we know that is paper 1, which has the structural questions, and basically you have to write your answers within the question paper. And of course, it's made up of 2 sections. And of course, we have paper 2, which is made up of the theoretical questions. And of course, we have both sections, still both section A and B. And then of course, we have the paper 3 that is made up of the more concept bits, the inorganic qualitative analysis, and then we also have the organic quantitative analysis. So today our discussion will basically cut across any areas, but I had really prepared to share from the view of paper 2, but we can always share on both extremes. Okay, thank you, Mr. Kaira. I can see your hand in the chat. Mr. Kaziba, I don't know if he's still on call. Is it possible to grant those teachers co-host rights just in case they want to chip in something, they don't have to raise their hands? I don't know if that is possible. Okay, so we also understand that paper 2, since we are Form 6s, at least we've encountered this paper for quite some time. And I know at your schools you may be doing different tests to really acquaint yourselves with this paper. So of course, we know paper 2 is made up of 8 questions. And these 8 questions, of course, comprise of the physical chemistry having more of the numbers, which are 3, and then we have the inorganic, which has 2, then the organic, which also has 2 questions. But of course, the 8th question usually has a mixture. It may be picked from all the sections. At least you have to combine knowledge to explain the different observations. You may have the organic and then the inorganic, and of course apply also some principles of the physical chemistry. So this slide is basically showing that outline. We have 4 questions in section A, of which you're required to do 3 questions from that section. And then you also have 4 questions in section B, where you're required to do at least, sorry, not at least, to do 2 questions from there. So like I've said, we have 2 from organic, 2 from inorganic, 3 from physical. I wrote 4 here because the observations, and those observations cut across. It may be the inorganic, all those questions may be there. You may find that they're telling you to explain those observations like in 4 different categories, and maybe the 2 questions are from organic, 2 are from inorganic, and then maybe 1 where you have to incorporate the physical knowledge. Okay, so I prepared some questions that I want us to discuss. I don't know if the teachers have something to say about the comprising of the papers before we discuss some of the questions I had prepared, as we also come along with some questions. And of course, I'll be requesting us to participate so that I am not the only one talking throughout. So as the questions are displayed, I would expect our audience to participate by contributing your answers either in the chat or by raising your hand. I don't know if Mr. Kaila would want to say something before I continue to the questions. Or any teacher in the audience. Okay, I think that's all. We can go ahead and discuss our first question. Our first question is coming from the inorganic bit of chemistry. And of course, it's telling us the atomic numbers of scandium and manganese are 21, 21 and 25 respectively. So we are requested to write the electronic configuration of scandium. Can we have some contributions in the chat, or you can raise your hand and we see your contributions? I can request you to unmute so that you contribute. So we have the atomic number of scandium as 21. Who can write for us the electronic configuration of scandium? I don't know, am I being heard, or is it that I'm just not seeing the people on raising their hands? Because I don't seem to be getting any feedback. Okay, thank you, Pinako. So why aren't I getting feedback? I don't know why. So can we kindly contribute? Because like I said, I don't want to be the one doing most of the talking. Okay, I can see Ivara SS. Ivara SS, you can unmute.
Yes, I'm trying the electronic configuration for scandium. It is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 4p1.
Can you please redo that?
Okay. 3d1 is the last quantum number.
3P? No, please redo the whole configuration because I want to note it down here as you say it.
Okay, it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 4d1, 3d1 I mean.
Okay, thank you. So that is your suggestion. Thank you, Ivara SS. Can we hear from Act High School?
Thank you. Hope you are listening to me. Mine is 1s squared, 2s squared. Then, sorry, let me repeat it. 2s2, 2p6, 3s2, 3p6, 3d1, and 4s2.
Okay, thank you, Act High School. So these are the two configurations we have, but of course we know that when we add each of the values on top of the suborbitals, we need to have a total of the atomic number that was given to us. So that means if we have 2 plus 2, then that is 10, that is 6, 18, 19, 20, 21. So that means this becomes the correct configuration of scandium. And also there are instances where you can start with the 4s and then the 3d comes last. So whichever you may want to start with, there can work out. Then I am seeing something in the chat that I think we should share before we move on. Someone is saying we are not seeing the question. Maybe you try to log off and then back. So paper 3 isn't entirely mole concept as question 1. It can be from thermochemistry. So, oh yeah, thank you for that correction. It can be any question from the physical chemistry part. So question 1 of paper 3 can be any physical chemistry question. So it can be thermochemistry, colligative properties, volumetric analysis, or chemical kinetics. So I think when I was saying paper 3, I said more concept only. So it covers any practical part of the physical chemistry branch. So you prepare for any of those, because any of those can appear as your question 1. Okay, so what is the electronic configuration of manganese? And then, of course, as you work out their electrical configuration, you can also work out for their ions, for scandium 3, and then manganese 7. So for scandium, we said you can have this or have the 3d orbital come before the 4s orbital in arranging them. Yes, Act. Act High School, you can unmute.
Yes, it is 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s2.
Okay, thank you so much, Act High School. So that is the configuration of manganese. And I've been seeing Rega putting up his hand. Rega, can you share with us what the configuration of scandium 3 ions is? So here still the same thing can happen. You can start with a 3D and then the 4s as your last orbital.
So to come up 3p6 for iron 3 scandium 3.
We are dominating on the right. P6.
Since we already have the configuration for scandium, is there someone that can get for us the one for scandium 3 ions? I can see a hand up. If I need to know I'm talking to people because I'm seeing only ACT High School raising up the hand. Are there things too simple that we don't want to contribute, or just Rebecca? You can unmute.
The scandium 3 ion is 1s2, 2s2, 2p6, 3s2, 3p6.
Two P6, 3s2, and then 3p6. And I hope we all agree, because you realize that if it's made up of 3 ions, that means it has lost the 3 ions in its outermost energy level. So that means the 3 electrons in the last 2 subatomic orbitals, you find that those 3 electrons are being lost, and then we are able to remain with the configuration with the 3p subatomic orbital as our last orbital there. Okay, then we move on to the next. Manganese 7 ions. What is going to be the configuration?
It stops on 3 manganese.
This is 7.
Yes, Napak Seed School.
It is manganese 7 ions. It is 1 squared, 2s squared, 2p6, 3s squared, and then 3p6.
Then 3p6. Okay, thank you. So you notice that for the manganese, since it's 7 ions, that means the last 2 7 electrons in the last 2 subatomic orbitals is lost, and then we are remaining with the 3p6 as our last subatomic orbital. Okay, so Coach Girls Secondary School, they are saying they are not seeing my screen. Is it possible for you to log off and then log back in? Oh, everyone is not able to see my screen.
Yes.
Are we able to see my screen, the rest of us? I think since ACT and NAPAC, since your microphones are open, you can give me feedback. Are you able to see my screen?
Yes, we're seeing you clearly.
Okay, so then Okacha, I think it's Okacha Girls. Please kindly, you can log off and then try to log back and see. Okay, thank you. So I don't know if the teachers have something more to add on to this information that we've written down here, because we'd love to move to the next part.
It is already open.
All right, I wanted some explanation basing on actually the electrons, how they occupy the orbitals.
Sorry?
Most especially, there is a tendency of overlap, and so that issue of arranging the last orbitals in the last energy level, you find that some transition elements, there is a way they take that tendency that we need again to arrange them to make sure that they fit.
Okay, what rules do we use when feeding those energy levels? Yeah, of course, Afobos principle is one of them. Which other principles do we use when feeling the energy levels?
There is actually a answer rule.
You're not sure of the rule yourself, eh?
Yes.
Okay, so I'll request any teachers here, Pinnacle Chemist or Mr. Kaira, are you willing to guide our learners on how we can go about that feeling of energy levels in case we come to instances where there is an overlap of those electrons? Nampak, your hand is up. Is a teacher willing to contribute, or it's the student still? Oh, okay. Thank you, Mr. Kaira. So of course, as those energy levels are being filled, you need to understand the flow of those energy levels. I know at the beginning of your writing of these configurations, your teachers took you through that process of how the different energy levels are arranged and how we expect each filling to happen. And of course, we know when we come to the p orbitals, they usually get filled with 6 electrons in them. And when you get to the s subatomic orbit, sorry, on the s orbital, you realize that we have 2 electrons in our field. That is why you find that a configuration will flow in that accord, that when you're coming from the 1s subatomic orbital, you come in with that 2s. And of course, if the electrons are more than the number that you've already filled, you keep on topping on that. So if the second level of those energy levels is filled, obviously you're going to move to the what? To the third energy level. But we know that the 4s energy level gets filled before we move to the what? To the 3D energy level. So that is why in most cases you find that it has a completely filled energy level before the 3D orbital. So that is something you need to take note of. Okay, so we have this next question. We are explaining why scandium only forms compounds in its oxidation state of 3, while manganese forms compounds in which its oxidation states are +2 and then +3. So when you're ready to share, you can please raise your hand and then we'll request you to unmute. Those with questions, kindly, you can raise your hand or post your answer in the chat. And if there is any teacher who wants to add on to the information that we are sharing, kindly feel free to share in the chat so that we can share your thoughts. And if you're interested in unmuting, you can as well inbox me in the chat and we can request you to unmute. Yes, Vera SS.
Okay, according to me, this explanation will be based on the number of electrons the elements lose in order to form the ions. For scandium, it is in oxidation state of +3 because it loses 2 electrons from the 4s suborbital and 1 electron from the 3d suborbital. Those are 3 electrons lost, so that's why it is able to form oxidation state of +3. Meanwhile, for manganese, manganese is able to form the oxidation state of +2 and +7 because it loses 2 electrons from the 4s suborbital and the 5 electrons from the 3d suborbital, forming the when it loses 2 electrons from the 4s suborbital, it is able to form the oxidation state of +2. And for 7, it will lose 2 electrons from the 4s suborbital and 5 electrons from the 3d suborbital, which makes it to form oxidation state of +7.
Okay, thank you. That is so good. Let's hear from Jemobiru. Jemobiru, you can kindly unmute.
I think scandium, according to electron configuration groups, it has 1 electron in the 3d orbital, the 4s. So it can only use those ones when forming compounds, where it can only use those ones when forming compounds. And in manganese, since it has 3d5 and 4s1, so it can lose that one of, and it cannot come from the s orbital of 4. So it can form stable compounds in the +2 and the +7.
Okay, thank you. That is good. Any more contributions that are different from that? Gus, your hand is still up. You have something to add? Guys, I'm not hearing anything from your end. I don't know if you're talking or you're not. Okay, let's hear from Gayaza, Adventist.
This is because it is because scandium has
I think there is someone with an unmuted mic that side. Maybe if they could step out or mute for now as you contribute. Okay, please go ahead.
It is because scandium has no covalent field in the orbital.
As an Adventist, there is a lot of feedback coming through. I think there are some microphones that are open that side. Okay, lastly, let's hear from ACT so that we can move on to the next part of this question.
Thank you. I think for the scandium ion, it has 3 electrons in the same orbital. Instead of being with 12, it has 3. So it is easy to easily lose the 3 electrons. And for the manganese, it has 7 electrons in the same orbital, and it is very easy to lose the 2 electrons from the 4s, and it retains 5 electrons from the 3d because it is thermodynamically stable. Thank you.
Okay, thank you. That is good. So I can see that we all have clues on how to go about this question. So, of course, we know that scandium loses 2 electrons. This is very key for you to note. 2 electrons of the 4s orbital and 1 electron of the 3d orbital. Like we saw in the configuration, we saw that the configuration ends with the 4s2 and 3d1. Or we said you can start with the d and then the 4s comes last. So we have that, and once it loses these 3 electrons, that means it's able to form compounds with the oxidation state 3. And then, of course, when we have, you realize that once it loses these 3 electrons, it remains with the 3p6. And we know for the p orbital to be completely filled, it should have 6 electrons in it. So that makes it stable because it's ending with a stable kind of configuration, and its outermost sub-energy level is completely filled, hence making it stable. And then, of course, when we go to the manganese, we know that manganese is able to lose the 2 electrons of the 4s orbital, and then, of course, the 5 electrons of the 3d. So if we've lost 2 plus the 5 that are lost from the 3d, that means it leaves us with a 3p6 sub-energy level, which is full of electrons, and that makes it what? Stable. And therefore it can form the compounds with a manganese 7 kind of oxidation state. And then, of course, when we move to the 2p, and then, of course, we understand that when manganese loses the 2 electrons, it's going to lose them from the 4s orbital. And when it loses those 2 electrons from the 4s orbital, it remains with the 3d, which is partially filled and makes the what? And it is able to make the compound stable as well in order to form compounds with other elements. Okay, so there is an emphasis here. When you're writing these ions, they should be written in capital Romans and not the small Roman numerals. So you ensure to take note of the ion, the scandium 3, and then the manganese 7. Ensure to write them as capital Roman numerals. Thank you, Mr. Kaira. So it's important for you to take note of that observation. As you're writing those ions, describe them as capital and not as small. So I hope we've understood that bit of the electrons that are being lost to form stable compounds. They are able to lose those electrons respectively. Okay, I don't know if someone has a question or we can continue. Yes, I can see some hands up. I don't know if there are contributions or questions. Let's hear from Kanjuchi.
Okay. Yes, thank you. There is some argument we are having here when you're denoting the electronic configuration. Sometimes when you follow Aufbauer's principle, 4s comes first before 3d. But in most texts, we see 3d coming first before 4s. What is considered? I mean, what is right? Is it that when you're writing the electronic configuration, you should only and only follow Aufbauer's principle, or you can do otherwise?
Okay, thank you for that question. Anyone who can help us respond to that question before I give my thoughts? ACT, are you giving us a response to that question? ACT High School?
Okay, thank you. Like, when we follow the principle, yes, we see that the 4s is filled before the 3d. But remember, the 4s and the 3d are in the same orbital. Then in most cases, for transition elements, we say that there is an overlap. When an overlap occurs, the 3d orbital is filled before the 4s orbital. I think that's the reason. Then there is the other question, because I thought it is necessary to give a reason as to why, in the case of manganese, where we are forming the oxidation state of 2+, I thought it is necessary that we give a reason as to why we are losing the 2 electrons on the 4s orbital, and we are remaining with the 5 electrons on the 3d orbital in our explanation. Because according to we thought it is simply because the 3d orbital is halfway filled or partially filled, that it is thermodynamically stable. What?
Yes, and that is true.
Thank you.
So if you're following in the chart, you can realize that both approaches are okay and you can begin with either. And I think Kanjuchi, S.6 joined a bit late because we had emphasized that. So when you're filling the orbitals, of course, you're following the principle, but you can start with either the 3D or the 4S. So while writing them, it's okay for you to begin with either of those. Okay, so I think there are no questions and we can move on. So we have another question here. And like we said, of course, this is not the only question that will come in inorganic, but as you notice the trends of your papers, you realize that any question from inorganic can appear in section A. So that means you should be well versed with the trends, the different transition elements that are within your scope of study, and there are trends in boiling point, there are oxides, the hydroxides, and there are different reactions. Okay, someone is saying I suggest about the writing of sub-energy levels, 3P sub-energy level and non-3P6. Okay, thank you for that observation. The explanation for manganese is not complete. I don't know the screen on what we are discussing. Richard, I need clarity on that because while explaining, I completed it because on the screen it wouldn't, because of the size of the letters, it couldn't finish. But I think when I was explaining, I completed it. Okay, so we have this question here. Can we get our thoughts on what we think? So any thoughts for us here? The question is telling us potassium hydroxide was fused with manganese 4 oxide. Was fused with manganese 4 oxide in the presence of oxygen to form a green solid X, and was dissolved in water to form a green solution. On bubbling with carbon dioxide gas through the green solution, the purple solution Y and the brown solid were formed. Okay, let's hear from URDT.
Okay. I think the green solid is
potassium manganate 6. And the equation for the reaction, 4 moles of potassium hydroxide reacted with 2 moles of manganese 4 oxide and 1 mole of oxygen, producing 2 moles of potassium manganate 6 and 2 moles of water.
Okay, thank you so much. You are a DT. That is good. So I see the other hand has gone down. That means they concur with what you said. And please, I will request us to follow the chart as well, because some of the suggestions are being made there by some of the teachers. So kindly follow through and you're able to get enlightenment on some of those questions. Okay, so of course, the solid X that is being formed is the potassium magnet 7. Sorry, magnet 6. So the equation, like you said, we have the 4 moles of the hydroxide plus the manganese 4 oxide plus the oxygen to give us the potassium magnet 6 plus the what? Plus 2 moles of water. Of course, there is an arrow here. So the question further goes ahead to say, write the equation leading to the formation of solution Y. And we've been told that after forming solution X, it was dissolved in water to form a green solution. And on bubbling the carbon dioxide gas through the green solution, a purple solution Y and brown solid were formed. So what equation is leading to the formation of the purple solution? And what is the purple solution that is being formed there? Okay, someone is asking for the half equation for the previous. Okay, so we are going to have the half equation for the reaction of the hydroxide with the manganese oxide. And of course, we have the hydroxide ions. Hope they'll be able to fit here. We have the hydroxide ions. Reacting with the manganese 4. Plus the oxygen gas. To give us the magnet ions. This is an aqueous state plus water. And of course, you balance the equation by having 4 moles of the hydroxide and then 2 moles of the manganese oxide. And then, of course, we have 2 moles of the ions and then 2 moles of water. So that is the ionic equation for the formation of the potassium magnet 6. I hope you're able to observe my screen as well. And then, of course, there is a question we're answering. How can we obtain the purple solution, and what is the purple solution that we are obtaining from there? Oh, sorry about that. I just wanted to ensure that my letters can fit within the slideshow description. So the question is right there. Anyone that had come up with the equation? Yes, Mobiru? Mobiru, you can unmute and share.
So the formation of formation of solution Y, we say that 3 moles of potassium manganate 6 aqueous plus 2 moles of carbonate 7. Yeah. Potassium aqueous. And solution Y is potassium.
Mobiru, I don't seem to get you. You're breaking. I can hear potassium, permanganate, then magnet, but I'm not getting. I don't know if it's on my end, but I'm not getting your clear explanation on the equation you're getting there. Okay, I don't know if you're still on. So of course, someone in the chat is someone is requesting for the questions. I think Mr. Kaziwa will share them. I will share them with him and he'll share them. Then Amanya is saying when magnet 6 ions are bubbled through carbon dioxide, it disproportionates to magnet 7 ions, which are a purple solution, and then magnesium oxide, which is a brown solution, and the carbonate. Okay, that is good. Yes, the hydroxide is in solid state. Yes, Innocent.
On that number one, that one where we are getting potassium manganate 6, we expect that potassium manganate 6 to be a solid, but we are seeing on ionic equation that potassium manganate 6 ionizing, and we are not getting there.
Here on this ionic one.
Yeah, on that potassium manganate 6, which is a solid. On ionic equation, we expect it not to ionize.
So we expect it to remain as a solid.
Yeah. But I don't know whether it's true.
Okay, can we get some feedback from the rest of the teachers? What do we expect at the end of this ionic equation? Do we expect it to ionize or to remain as a solid at the end of the day? Okay, so it will remain as a solid, not as an aqueous. So it will be a solid. Thank you for that correction. So here we have the formation of the permanganate, which will give us Okay, sorry about that. So here we have the purple solution, which is the permanganate solution, and then of course we have the manganese oxide, and then we also have the carbonate ions being formed at the end of that reaction. So of course the brown solid is this here, and then we have the purple solution as this. Okay, so we are moving to our next part of the question. So we have why when sulfur dioxide was bubbled through acidified solution, why the color of the solution turned from purple to colorless. And we identified solution Y as potassium magnate 6. So the question is asking us when sulfur dioxide was bubbled through acidified solution Y, The color of the solution turned from purple to colorless. Who can explain to us why? The question is on the screen unless it's not being shown. But we found out in the previous slide that solution Y, or the substance Y that was produced was potassium manganate 6. So the question is asking us the color of that solution. Oh no, sorry, that was X. So why we notice that it's potassium permanganate. So the potassium permanganate turned from purple to colorless on being bubbled through sulfur dioxide. Why was that? So why did it turn from purple to colorless? Oh, okay. Are you able to see the question now? Let me see if I can try to increase the font. Let me try to increase the font and see. Is the font now more visible? Okay, so can we go ahead and answer the question? Yes, you are, TD. Okay, let's hear from Lansana St. Joseph.
Manganese manganese 7 is an oxidizing agent. It oxidizes sulfur dioxide to a sulfate, and itself gets reduced to manganate 2 ions, which are colorless ions.
Okay, thank you, St. Joseph. Any other contribution? Gumu Jamia, I think maybe you need to log off then back because it seems the rest are seeing my screen, so I don't know what the problem would be on your end. You may need to log off and then back. So we have sulfur dioxide reduces the magnets 7 ions to the manganese 2 ions. St. Joseph, your hand is still up. Do you have a question or a contribution? You just forgot the hand up. So I was still saying, so someone is asking, are we supposed to write it in past tense? The question has to guide you because remember the question was reported to you in past tense and they asked when sulfur dioxide was bubbled through. So that means definitely your answer should also present the kind of tense the question is guiding you to give. So they said when sulfur dioxide was bubbled through the acidified solution of Y, the color of the solution turned from this to that. So that means even you're reporting what happened. Why did it turn that kind? So that means it reduced the magnet ions to the manganese 2 ions. And like you can see in the equation. Well, this is supposed to be sulfur dioxide. Sorry. I think it was a typing error. It's supposed to be sulfur dioxide. Innocent, your hand was up. So please make that correction. It was a typing oversight. It's supposed to be sulfur dioxide and not sulfite ions. So please change this. It should be sulfur dioxide. Okay, so basically that was it about question 1. And like I shared, that question 1 can come from any part, but you have to notice that you know that different transition elements, their trends, their melting point, especially for group 1, group 2, the trends of their boiling points in oxides, in hydroxides, and of course, sometimes you may be expected to draw the graph. Yes, it's in gaseous state, of course, because if we change it to sulfur dioxide, then it will be gas. So it will be sulfur dioxide gas plus water to give you the manganese ions and then the sulfate ions plus the hydrogen ions. So please, as you write, you make that correction. I don't know if the teachers within the audience have something to top on to number 1 before we move on to the next number. Napak?
All right, madam. To me, I thought on the right, on the left-hand side, you had a manganese 7 plus sulfur dioxide and then hydrogen ions. So that on the right-hand side, you form manganese 2 ions, then and water. But now from the other side, it is contradicting. All right.
Thank you. Like I said, we have the magnet ions this side on the right, on the left-hand side, plus the sulfur dioxide, plus the water. For the other side, for you to be able to form the manganese 2 ions, and then the sulfate ions, plus the hydrogen ions. But then if you choose to bring the hydrogen ions on the left-hand side, that means on the other side of your equation, you're going to have water being formed. That's if the hydrogen ions are on the left-hand side of the equation. So it has to depend on what reactants you have on the right-hand or the left-hand side in order to obtain the products on the right-hand side. So if you have hydrogen ions on the left, definitely it will call for water as your product. Okay, so I'm seeing some comments in the chat. May I please have the half equation? Then Mr. Kaira is asking the learner should tell us what happened to the sulfur dioxide for a complete explanation. Can someone tell us what happens to the sulfur dioxide? I suggest as you write the equation, when the space on the right side is over, write the other products under. But yes, my equation just went there because I needed to enlarge the letters. Just a minute. So URDT is telling us sulfur dioxide is oxidized to sulfate ions. Okay. And I'm seeing some hands. Mvara S.6, please unmute.
Yeah, the sulfur dioxide is oxidized actually to sulfate ion, since what we have is a redox equation, and the permanganate ions themselves are reduced to manganese 2 ions. Thank you.
Okay, that is very good. Thank you. Origin, is it origin?
Thank you, madam. I think sulfur dioxide, this equation is an oxidizing agent at the same time reducing agent, redox equation. So itself is oxidized to sulfate ion, and then it reduces the manganate 7 to manganate 2, as shown in the equation.
Okay, thank you. That is good. Let's hear lastly from Nansana.
Excuse me, madam. If I want to use sulfite ions on that very question, and I use this equation that 2 moles of manganate 7 react with 5 moles of sulfite ions in aqueous plus 6 hydrogen ions aqueous, giving us 2 moles of manganese 2 plus 5 moles of sulfate plus 3 moles of water. Can I be marked correct?
Please repeat that equation so that I can share it and people can give us their suggestions on what they think. Please unmute and repeat the equation.
Two moles of manganate 7 plus 5 moles of sulfite plus 6 hydrogen ions, giving us 2 moles of plus 6 hydrogen ions, giving us 2 moles of manganese 2 plus 5 moles of sulfate plus 3 moles of water.
People, is this correct? We can give our thoughts. I'm waiting for our responses. Okay, I'm seeing Napak.
Thank you, madam. What we want to get clarified is that, are we reacting sulfur dioxide or we are reacting a sulfite ion? Because in the question, it is very clear that sulfur dioxide was bubbled through acidified solution. Why? Now, to me, it is becoming confusing seeing in the equation we are bringing on board, sulfite reacting with the permanganate. Let's make some highlight on that we should be clarified.
But she's also asking a question. That is that equation correct? That was her question.
But now if it was to react with the sulfide, the question was going to qualify. But now the question is not rhyming with what we are supposed to put right. We are supposed to make a right equation for a sulfur dioxide, not for the sulfide. If they had asked for the sulfate reacting like that, that means the equation was going to be correct.
And I think she has to put it to there instead of there.
Okay, thank you so much for that feedback. Let's hear from Vara.
Yes, well, if you read the question part B, reading the question, it reads, when sulfur dioxide was bubbled through. So based on that, I think we should write an equation for sulfur dioxide, not sulfite ion. That is actually my contribution, because the whole thing will appear like we are now setting and doing our own question. Thank you.
Okay, thank you. So I think we need to stick to the question here. Let's hear from URTD. We need to stick to what the question is requesting us to use, the sulfur dioxide being bubbled through the acidified permanganate plus the water to give us the corresponding ions. Yes, URTD.
I think that 2 moles of the manganate 7 ions will react with 5 moles of sulfur dioxide and 2 moles of water, giving 5 moles of the sulfate ion and 5 moles of the manganese 2 ions plus 4 moles of the hydrogen ions.
Okay, so we stick to this equation on our screen. Our dear student from Nansana, so please stick to that response on the screen. So I would want us to move to our next question of discussion this evening. Okay, so we have our next question here. State what would be observed and write the equation for the reaction that would take place if the resultant solution in D was added to dilute sodium hydroxide solution. So maybe here, since we already have the responses on the screen, I would want an explanation from any of us on why the white precipitate turns brown on standing and and if those equations are correct and why they are formed that way. So maybe that's a feedback I would request from us. So this is our next question. Because our time is really fast spent, I request we move to the next question. I hope at least we're able to take note of what was on that last number, and we can further our discussion. Okay, so can I get some feedback from us concerning this question? Yes, Napa?
Partition coefficient is the ratio. Is the ratio of the molar concentration of two immiscible liquids that are in contact at equilibrium, provided that the solute does not dissolve between two immiscible liquids. All right.
Okay, thank you. Can we boost that definition? Yes, Nkata.
Partition coefficient. Partition coefficient is the constant ratio of molar concentration of a solid in two immiscible solvents mixed together, in which it is soluble in both at constant temperature.
Okay, thank you. That is good. Any other contributions? Yes, Siga, please raise your hand if you want to say something. Otherwise, we cannot unmute everyone to keep talking. Okay, I'll see some hands up. Let's hear from Gayaza Advent. Sorry, I have to just put your hand down. Sorry. You can raise your hand again, Gayaza Adventist. As you do that, let's hear from ACT High School.
Thank you.
Napak, can you please mute the microphone? Please go ahead.
Partition coefficient is the constant ratio in concentration of solute molecules in one immiscible solvent to the concentration of solute molecules in another immiscible solvent when two solvents are in contact with each other and the solute remains in the same molecular state in both solvents at constant temperature.
Thank you.
Thank you.
Okay, that is good. Thank you. Gayaza Adventist, then we'll hear from Vara, and then we can round up on that part.
According to me, partition coefficient is the ratio of distribution of a non-volatile solid in two immiscible liquids with the same molecular state at constant temperature.
Okay, thank you. Vara.
Yes, I think partition coefficient is the constant ratio of the molar concentration of a solid in between two immiscible liquids that are in contact, at a constant temperature.
Okay, thank you. So at least there is something common about all our definitions. So we have partition coefficient as a constant ratio of concentrations of a solute between two miscible liquid solvents in the same container at the same temperature. Because remember, if this, we have the concentration of the solute and these two immiscible liquids, and I am very sure all of us know what immiscible liquids are. So that means that solutes exists in both the immiscible liquids, and these immiscible liquids, of course, are in the same container and at the constant temperature. Okay, I'm seeing a hand up. Let's hear from Napa.
There is something, madam, I want to get clarified. We are saying that the partition coefficient is a constant ratio of the concentration of a solute between two immiscible liquids which are in contact, such that when equilibrium is attained, the molecular state of a solute in two solvents should remain the same. But now I'm not saying that, is that the molecular state of a solute going to be maintained in the two solvents after dissolving, or it's going to change? Because I considered that at equilibrium, to make it more sensible, that the solute should remain in the same molecular state.
Okay, thank you for that observation. Kanjuchi?
So thank you for the opportunity. I would like to supplement on our definition for partition coefficient. So partition coefficient is the ratio of the equilibrium concentration of a solute in a liquid solvent to the equilibrium concentration of the same solute in another solvent, provided the two solvents are immiscible and the solute is soluble in both solvents, and it remains in the same constant, in the same molecular state in the solvents at a given temperature.
The solution. Of course.
I think that is okay, but I think we are all rounding to the same definition, but in different phrasing. But it's all rounding up to what a partition coefficient is. Because basically, of course, you have these two liquids gaining equilibria when the solute has been, when the solute exists in both those immiscible liquids. And of course, we know immiscible liquids, we cannot tell them until they are placed in the same what? In the same container. So basically, we are all rotating about the same definition, but in different English or different what? Phrasing. Yes, James?
Thank you so much.
Thank you so much. Thank you so much. Thank you so much. Thank you so much.
James, we are not
Okay,
hearing. I am not hearing.
What is important here is you look at the two solvents. Those two solvents must be in contact with one another. Then, what they're talking about, the solid remain in the same molecular state, is that there should be no association or between the solvent and the solid.
Can you say that again? Then there is a question that people are debating about in the chat. Is partition coefficient calculated considering molar concentrations, or it can be calculated using any concentration depending on what you're looking for in that given coefficient? But I think we'll get there as we are calculating, so let's go step by step. So when we get to the calculation, the owner of that question can go ahead and ask. So we have our next question: state 4 conditions under which partition law is valid. What are the 4 conditions under which that partition law is valid? Okay, can we hear from Ayesiga? Ayesiga, please unmute.
The temperature must be constant.
The temperature must be constant and the solid must remain in the same molecular state. Thank you. Okay, let's hear from Kata. Sorry, I had gone off. I don't know why my network is misbehaving.
The first condition is the temperature should remain constant. The second condition, the two liquid solvents must be immiscible. The third one, the solid should remain in the same molecular state in the two solvents. Then the fourth one, the solid should not associate or dissociate in the two immiscible solvents. Thank you.
Okay, thank you. That was good. So all those conditions that he suggested were as he suggested them. So you've been listening in, please note them down. Now, of course, should not saturate one of the solvents is basically to do with should not dissolve in one of them. Yes, it's true. Ayesiga. They are the same. So let's move on to our next question. This one, I request that someone just gives us a summary of this experiment so that we can move faster. Okay, let's hear from Rega.
So with the experiment to determine the KD of iodine between ether and water, the first step we're going to get non-volume of ether. Then we mix it with iodine. When you mix with iodine, then you'll add non-volume of water. Next thing, you're going to shake. When you shake, then you leave, after shaking like for 5 minutes, you're going to leave it to settle. You leave it to settle, you're going to titrate a portion of the organic layer and titrate it with sodium thiosulfate using starch indicator. And then after all, you'll find that you actually determine the amount of the thiosulfate. So from the equation, it will be 2 to 1. So it will help you to find the concentration of iodine, of this iodine in the organic layer. After that, you'll do the same thing with the aqueous layer. Then you'll be able to find the concentration of iodine in the aqueous layer. From there, KD will be equal to, since it is ether and water, will be equal to concentration of the iodine in ether or organic layer over concentration of iodine in water. So by that, determine the KD or partition coefficient.
Okay, thank you so much, Rega. I think I couldn't say anything better. So is there someone with an alternative way on how we can determine the partition coefficient of ether with water? So the limitations can as well as be referred to as the conditions. I stand to be corrected if that's not true, but they should be giving you the same thing. So someone is requesting, maybe I can give some comments. Yes, Pinnacle, please let me try to search for you so that you can say something. Please, teachers in the audience, you can always request to say something since we are all muted. So you can please unmute Pinnacle chemist.
Oh, okay, thank you so much. Hopefully I'm audible enough.
Yes, please.
I would like to comment about that very experiment or any experiment. A student who is going to present that experiment, let the experiment be coherent, let it be logical, and let it be flowing very well. That's what I'm trying to mean. And the procedures must be connecting to each other so that you are showing this person that you are carrying out the experiment. And for example, the way how one of you has been able to give, if you get a known amount of iodine and you add it to a known amount of ether, probably where in a separating funnel, then you add in a certain amount of water to that very separating funnel, you shake it, you leave it to stand at a given temperature. Let the temperature be mentioned. If you leave it out, the experiment now becomes invalid. So, and the actual marking might stop there. Then after that, after settling, probably you pipette a known volume of the aqueous layer as well as the organic layer, and you titrate them with a standard solution of sodium thiosulfate, using a known indicator, that is starch indicator, and you calculate the concentrations of iodine in each layer. Then my observation is here, when you're giving the formula of KD, because you have to put it down afterwards, kindly always look at the question. The question says between ether and water. Don't make a mistake and you say between water and ether. That should be a good observation you should make in that experiment, because you might end up losing that full mark down there. Thank you so much. That's what I wanted to say.
Thank you so much, Pinnacle chemist. So I think that was very enlightening. And I would also continue to emphasize that take note of what the experiment asked for. So if it is ether and water, emphasize the KD to be equal to the concentration of iodine in ether over the concentration of iodine in water. Okay, so can someone suggest to us the equation we are supposed to write after explaining? And of course, those few things that Pinnacle chemist kept highlighting, they are very key for us to actually note. The masses should be known, the volumes, and then also the fixed temperatures, the pipetting, and then the titration using a standard solution, and then of course you state the solution, and then the starch indicator. And then after that, you can as well write the equation for that experiment. Who can detail for us what that equation will look like? Our next question is requesting for 4 reasons why ethoxyethane is most commonly used as a solvent. Yes, St. Joseph?
Ether is immiscible with water. Ether is immiscible with water. It is a good organic solvent. It is generally inert, hence it cannot react with most organic compounds. It is very volatile and hence can be distilled off or recovered after use.
Okay, thank you, St. Joseph. Any other contributions? So you realize that ether, as she said, is immiscible with water, and then of course it's a good organic solvent. And of course, it's very volatile and it's unreactive. So therefore, it cannot react with most of the organic what? Solvents. That is why it's preferably used. Okay, so we have part C. This one is a calculation number. And it's telling us the partition coefficient of a substance Z between methylbenzene and water is 12. Then calculate the mass of Z that would be extracted from 200 centimeters cubed of an aqueous solution containing 8.0 grams of Z by okay, for the reasons why we use ether, I said the first reason, first of all, it's immiscible with water. Then it's a good organic solvent. It is very volatile. And also, it is unreactive. So therefore, it doesn't react with most of the what? Of the organic substances. Because remember, when you're looking out for which solutes to use, you must consider its operation with the solvents in which you're going to add it to. So we have this calculation question here. I want us to go through it. And I think it will close our discussion for today. So they're telling us the partition coefficient. That means the KD is 12. And then, of course, we've been given calculate the mass of Z that would be extracted from 200 centimeters cubed of an aqueous solution containing 8 grams of Z by shaking it with 50 centimeters cubed of methylbenzene. So of course we need to know the mass of Z that was extracted out of the methylbenzene so that we can work with what we have. So that means we are going to let the mass and the mass of Z that was extracted from the methylbenzene. Because that's the many, I'm not going to write all of them. So maybe we can just follow through. B maybe X grams. But then they have told us that calculate the mass of Z that would be extracted from 200 centimeters cubed of an aqueous solution containing 8.0 grams of Z. So that means for us to know the mass of Z remaining in the water, since we know the one that has been extracted out of the methyl benzene, that means we get the total mass, which is 8 grams, minus the X, which is the mass extracted from the methyl benzene. So that means our mass of Z remaining in the water will be 8 minus X grams. Then, of course, we need to know the concentration of Z in methyl benzene. Concentration of Z in methyl benzene. To get its concentration, we need to get the mass divided by the volume, which is 50 centimeters cubed. Then, of course, the concentration of Z in water will be the mass that remained in the water divided by the volume, which is 200. So after getting that, we will denote the formula of KD, which is KD. Who can tell me what the formula of our KD here is going to be, looking at the question they have given us? And according to what we emphasized in the experiment, who can tell us what our formula for the KD is going to look like? Yes, Napa?
It will be the KD equals to the molar concentration in the organic layer over the molar concentration in the aqueous layer.
Okay, so we have the molar concentration of Z in methyl benzene. Like I said, just follow through because I may not be able to write everything. Then the concentration of Z in water. So you can even see in the question, they started with methyl benzene and then they went to what? To the water. So can we calculate the answer? What answer will we get as I take Innocent's hand? So calculate the mass of Z that was dissolved. The microphone is already unmuted, so please share.
All right, we are considering that KD because we are seeing KD is greater than 2, and we are told that when KD is greater than 2, we shall always say that the concentration of maybe Z in aqueous layer over concentration of Z in organic layer, since the KD is greater than 2.
Okay, and there are some teachers here to give us more clarity on that. I'm not very certain because that he's asking that they were told if the KD is greater than 2, they instead say KD is equal to concentration of Z in the aqueous solution over the concentration of Z in methyl benzene. So I'm not very sure of how I should respond to that, so I don't know if the teachers here can say something. Please unmute.
Basically, when you look, every question you have to follow with what was given. When you look at the question and it says that the kid between this and this, so you should begin with what was given, not to change whether it is less than 2 or greater than 2. You follow what was given between this and this. If they say between water, you begin with water. If it is between methyl benzene, you begin with methyl benzene. That is my submission.
Okay, thank you so much. Let's hear from Vincent Muji. Vincent, you can please unmute. Okay, so since our time is fast, yes, please. Okay, go ahead.
Show of and aqueous greater than 2, it simply means layer than the aqueous layer. And that one means that it should be maintained. It is not a reason as to why we should layer. I think the formula still stands. Thank you.
Thank you so much, Vincent. So the formula will still stand, and I've seen some responses in the chat. People are saying 6 the grams are 6 grams. Thank you for calculating that. So the rest of the questions will be shared with you. I'll share them with Mr. Kasiva, and he will share them with you. And then, of course, you can go ahead and calculate Roman 2. And then, of course, you comment on your answers. But before we close, what are some other applications of this partition law apart from solvent extraction? Where else can we find its application? Maybe we can close with that. Yes, Mvara.
Yeah, besides what we have currently on board, other applications of partition coefficient include chromatography, and then there's determination of the formula of a complex ion.
Okay, thank you. Okay, so sorry. I went off when Pinnacle's hand was up, and I'm seeing some question in the chat. And of course, when you calculate the successive concentrations, you realize that the successive concentrations will give you a different mass from one particular extraction. So which one do we expect to have a bigger mass extracted? The one extracted from successive portions or one extracted from one large volume? Because even when you look at the question, it's catering for you having an extraction from one big volume, and then we also have part B giving us the successive portions. So you're going to realize that when you carry out the successive portion, it's going to give you a different mass or a slightly different mass from the one you have on a large volume. So which of the two give you a bigger mass and why? Maybe we can answer that question in closure. I don't know if Pina Kokemi still has something to say, because before I went off, his hand was up, but I can no longer see him. So I don't know if he still wants to say something. Okay, his hand is still here. So before I request you to unmute kindly, can I get a response from the rest of the audience, the students, basically? Okay, I think I'll just allow Pinako to talk. Okay, please, you can unmute.
Oh, okay, thank you. Sorry for taking you back a bit. I just want to comment on the calculated value where you calculate. Usually I've seen students making a mistake. They rush on that question. When they say calculate the mass extracted or calculate, because the question can be phrased in a different way, that calculate the mass which would remain in the aqueous layer. And the students, they usually rush and they go to calculate the mass which was extracted instead of the mass which would remain. So students, they have to be careful when they are reading that question. Kindly read the question 2 times in such a scenario. Thank you.
Okay, thank you so much, Pinako. That was very insightful. So I hope we've had that advice. And of course, the question I asked last, when you look at the successive, I'm seeing someone answered here. Thank you, Innocent. We obtain more mass from the successive portions than once. So that is very true. You realize that when you calculate part B, and after getting the two masses and you add them together, you realize that there will be slightly more than the what? The actual mass that you get when you use one volume at once. So when you split it into those successive portions, you're able to get a what? A bigger volume of the solvent, sorry, of the solute that you're extracting. Otherwise, thank you so much for being a good audience. It was good having you all, the teachers that joined in. Thank you so much. And thank you for sharing with the students. All the students, the schools, and everyone that saw to this seminar happening. Thank you so much, Mr. Kaziba. Over to you.
Thank you so much, Teacher Martha, for the wonderful session you have been able to offer this evening. Thank you so much. We are really very grateful for the service. I want also to thank all those teachers that have been on the call. Thank you so much. I saw Teacher Pinnacle, the chemist. I saw teacher, there's another teacher I saw. But thank you, Teacher Jobs and other teachers. And thank you so much, dear students, for keeping online. And next week, we are going to share the timetable we are going to be following for next week. But next week are some of the subjects that we shall have. We shall have economics. We shall have We shall have economics, we shall have some biology, we shall have history, we shall have physics, we shall have geography. That is coming in next week. So kindly prepare such that you can be able to attend all those sessions. We want to thank you so much, and we want to pray for you that everything goes on well as you prepare in for your mock examination, but most importantly, your final examination. We still have very few months to go, and we must utilize this remaining time to maximize and read as much as we can. We want to wish you a good evening, and thank you so much once again, Teacher Martha, and all the schools and the administrators that have been able to join. We wish you a good evening. Bye-bye, everyone.